In this video, I'm going to show the image of why we need a thermal TX driver in the SerDes system. As we will describe the impedance matching in the high-voltage mode driver video, the switches or the inverters in the voltage mode driver must be properly sized, such that their large signal equivalent turn-on resistance M1 3's R on N and M2 4's R on P are equal to 50 ohm respectively. Unfortunately, the active device PVT variations or mismatch would not provide a good enough impedance matching robustly. Therefore, many complicated calibration techniques are needed. In addition, the big swing may change the switch's biasing operating point over time and then modulate the switch's impedance. The impedance nonlinearity could cause a big reflection or ring over time at the TX output interface, and the nonlinearity must be taken carefully in the design. As we know, the active switches turn-on resistance are proportional to the inverse of their VGS or overdrive voltages, as shown here, which highly depends on the supply voltage. To make sure the switch's impedance is low enough or close to the 50 ohm, the supply should be big enough. Otherwise, the transistor impedance could be much big under the limited supply constraint. If the supply or the overdrive voltage is not big enough to reduce the switch impedance, what can we do? Think about the sizing images for 5 seconds. Correct. You could increase the width of the device as big as possible, and then the turn-on resistance would drop to 50 ohm, even though the supply voltage is too low. Do you see any issue with that? Think about your capacitance images for 5 seconds. Bingo. A bigger device leads to a bigger device capacitance and a passive capacitance. Therefore, the speed would be limited and the power would increase a lot with the CVF current consumption. Remember, the ideal power of the voltage mode driver would be 1/4 of the current mode driver, but the sizing overhead may reduce the power saving a lot and could be only 1/2 power saving of the current mode driver. After understanding the impedance matching issue of a voltage mode driver, let's think about the high impedance image of the current mode driver. As you know, a good current source must keep the transistor state in the saturation region, which should make the impedance close to infinity ideally. With the no-turn equivalent for simplicity, the output impedance ZL would equal to RS if the current source impedance ZCS equal to infinity or much bigger than the RS. Then the complete current mode driver's parallel or output impedance would equal to R or Z0 easily. Again, making the device impedance as high as possible in a parallel configuration is easier than making the device impedance as low as possible in a series configuration. In addition to a less design challenge of the impedance matching in the current mode driver, what else could be the impedance image of the voltage mode driver? Think about the supply or ground images for 5 seconds. Right, the voltage mode driver is very sensitive to any supply or ground noise through the series and pseudo differential arrangement. The supply noise image shows you that any noise from the supply or the ground will either modulate the switch significantly or pass through directly to the driver's output jitter or eye closure. On the other hand, the current mode driver is not sensitive to either the supply or ground noise through the parallel and fully differential signaling. For example, the supply VDD noise would be a common mode noise at both outputs, and the differential output Vout would have very little differential noise if the device mismatch was small enough. The high impedance of the active devices will isolate the differential ground noise significantly at the driver output Vout as well. So the signal integrity of the current mode driver might be better than the voltage mode driver without any design overhead. What else would you prefer using the current mode driver? Bingo! As we described in the TX driver video, changing the output swing is a must for meeting different SerDes usages or conditions. Unfortunately, the voltage mode driver's output swing will tie to the supply voltage VDD, which provides the maximum or large output swing, but not a small output swing. Therefore, this CMOS SSD driver will only realize a large swing driver without any flexibility. How could we realize a low swing voltage mode driver? Correct. All NMOS switches can still achieve a low swing voltage mode driver based on the push-pull operation. All NMOS switches SSD drivers can achieve several hundred millivolt swings, even designed properly. However, the impedance matching implementation with all NMOS devices is still a challenge. For example, if the input D is a logic 1, the M2 is at saturation region, and M3 is in the trial region, then the impedance of the M2's 1 over GM2 and the M3's turn-on resistance must be close to 50 ohm Z0 respectively. So the impedance matching of all NMOS switches still require very complicated calibration techniques over PVT and device mismatch, even though the output swing is small here. Do you see any issue with the swing control of the voltage mode driver? Yes, flexibility and reuse. As you can see, we cannot apply a single voltage mode driver for both very big and small swing easily. To save the area and output capacitance for high speed, no one would put two different drivers together in a multi-protocol SerDes application. Therefore, the voltage mode driver may limit the SerDes multi-protocol application. Then, we must separate both CMOS or all NMOS SSD drivers for different applications, which would have more design resource without any reuse advantage. On the other hand, the current mode driver is much simple to vary the output swing by only adjusting the output current, which is somehow independent of the supply voltage VDD if all transistors stays in saturation region. Therefore, we only need a single current mode driver to meet any multi-protocol SerDes swing requirement. The beauty of the design reuse would reduce the design resource and risk during the SerDes development or porting between different processes. From the previous discussion, you may realize that the voltage mode driver may have lots of design overhead even though the low power is very attractive. So the cost of the voltage mode driver is tremendous at the high speed and low power SerDes. For example, the signal integrity requirement is very tough in a high speed SerDes. So any circuit impairments in the voltage mode driver would degrade more quickly than the current mode driver. Maintaining a high impedance by keeping the transistor in saturation regions is always easier than keeping the low impedance in the trial regions. Any oversize of the added impedance will kill the whole voltage mode driver, which might not be caught easy in any thorough verification flow. Due to the design sensitivity and challenge, the voltage mode driver would normally has a higher risk than the kernel driver would. Not only the design resource, but also the design schedule in the virtual driver would result in a development cost much higher than the cost in the kernel driver. Here are a summarized image of why you need a kernel output driver in the SerDes system. We know why we need a virtual driver owing to its low power, which could be 1/4 of the kernel driver. However, the power is not the only design metric we care about. On the other hand, except for the low power, any multi-protocol SerDes can reuse the kernel driver with the impedance match over output swing control easily without any design overhead. The kernel driver provides a very good power supply rejection to achieve a very big eye opening in terms of big eye width and eye height for a very high speed SerDes. Since the kernel driver has a less design capacity than the virtual driver, but also has a higher design oversight tolerance than the virtual driver, the kernel driver's verification effort, design risk, and development schedule would be much lower than the virtual driver. Again, due to the design overhead of the virtual driver, the power might not be as low as what we expected. Instead, the virtual driver's power could be higher than the kernel driver if the whole design, including all the predrivers, impedance control, swing adjustment, and feed-forward equalizers were not designed properly. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.